The purpose of this video is to introduce the Wake-Glerkin finite element method. It includes two parts. The first part is about how to compute the WG finite element solution. The second part is about basic error analysis of the Wake-Glerkin finite element solution. Here we use equation 1 and 2 as our model, PDE model problem for simplicity. And equation 3 is a variation form for equation 1 and 2. Equation 3 is the starting point for the finite element method. Next, let's see what is the WG method. WG method starts with two important concepts of wake functions and the wake derivatives. First, let's see what is the wake function. We use this notation for wake function. Wake function means V equal to V0 and VB. That means V equal to V0 inside element T and V equal to VB on the boundary of element T. Look at that picture. So on the inside of a triangle, V equal to V0, this green surface. On the boundary, V equal to this VB, that green curve. So this is the notation for wake function. So you just need to know what that means. And the wake functions are defined on the whole domain. Obviously, they are totally discontinuous. After we defined wake functions, then we can derive our WG finite element space, VH here, define equation 4. VH consists of all the wake functions, and the V0 on each element T is a case order polynomial, and the VB on each edge of the element T, which is the boundary, part of a boundary, is a J's order polynomial. Since we consider homogeneous dirichlet boundary conditions, we let VB equal to 0 on the partial omega. Okay, that means the boundary of the whole domain. Okay, after we defined WG finite element space, then we can define wave gradient for them. Why we want to define wave gradient? Since all the wave functions, they are discontinuous. So we cannot take standard gradient for them over the whole domain. That's why we defined a wave gradient V, which is the approximation of the gradient. Okay, wave gradient V is belong to PST to this power. First of all, it's a vector. This means each component of it is an S-order polynomial. And the wave gradient V can be computed by equation 5. Equation 5 comes from the integration by parts formula. So something new here is, here we have V0, here I have VB. VB is not a trace of V0. And V0 and VB, they're totally independent. I like to mention that VB here is a single value on each edge, shared by both sides. Okay, I will show you how to compute wave gradient V for a given function V later, by examples. So after we define wave gradients, then we can define what is the WG method. WG method is find UH from VH such that equation 6 satisfied for all the V from VH. Bilinear form A here is defined in equation 7. So here, instead of a gradient UH gradient V, we have a wave gradient UH wave gradient V. because they are UH and V, they're totally discontinuous functions. And we need to plus a stabilizer, add stabilizer to make sure the problem is well, to make sure that equation 6 is well posed. The stabilizer defined like this. I like to mention the QB here is the L2 projection to the J's water polynomial defined on E. That's the space VB is in. And this QB, if U0 and UB, they use same degree of polynomial, we don't need QB there. So as you can see, the WG method is formed by two vector spaces. That's what we call WG element, the PK, T, PJE, and PST to the D's power. The first one, polynomial to approximate V0. The second one, to approximate VB. The third one is to approximate wake gradient. Okay, I like to mention that for the WG method, you see two equations, 5 and 6. What you need to do is to concentrate on equation 6. Equation 5, just a formula used to find the wave gradient in which. So to better understand what is the WG method, let's go back to the basic of finite element method. Okay, what is a finite element method? First of all, we need to find VH, which is a finite dimension. That's the key. Then we define bilinear form A there. They need to be well defined, such that equation A is well posed. So since VH is finite dimensional, that means it can be spanned as a finite number of basis functions. And UH belongs to VH, therefore UH can be write a linear combination of those basis functions. Then substitute UH to equation 8. Okay, since V here is any function in VH, what do we need to do? Just let V equal to those basis functions. For example, let V equal to phi1, you got a 1 equation. V equal to phi2, you got another equation. So we are going to get n equations and n unknowns. That's equation 9. Equation 9 defines a linear system. If it is a non-singular system, we can solve it. Find the CJ, put it back here, you find your finite element solution. So for the different definition of VH and the different bilinear form A, you got a different finite element method. For the continuous finite element method, the VH here includes piecewise continuous polynomials. Then the bilinear form A can be simply take the gradient phi j, gradient phi I. However, when your basis function phi j not continuous, then we cannot do equation 10. So that's why we have a WG method. For the WG method, the VH defined on the previous page. Then our bilinear form A is defined here. So if we are able to, so how do we find a weak looking finite element solution? First of all, we define the VH, right? Then we need to find its basis. Then we need to know how to compute wave gradient phi j. Then we need to know how to compute the stabilizer here. That's what we're going to see next. And the phi I here, they're all wave functions. They have two parts, phi I0 and phi IB. Next, I'm going to show you an example. How do we form a WG linear system? So for the simplicity, we consider this a simple WG element. That means V0 is approximated by first order polynomial. VB is approximated by 0 order polynomial. and the weight gradient is approximated by also 0 water per million in 2 dimensions. And our domain here is a unit square. Our triangulation for this case only have 2 elements, T1 and T2. And the VB here is 0 on the boundary. So only the edge associated with non-zero is this diagonal E here. All right, so that's our VH. So next, obviously, VH is a finite dimension. So what is the dimension? Now, V0 is a P1 polynomial on each element. They're totally not related. So P1, first order polynomial, 3 degrees of freedom on T1, and 3 degrees of freedom on T2 for P1. Then for VB is a P0. So on VB you only have 1 edge. So P0 is a degree 1 polynomial. I mean, it's a degree 1 on E. Therefore, the dimension of VH should be 7. In other words, VH can be write a linear combination of V1 to V7. The following is a sample basis functions. Now, phi1, phi2, phi3. Let's look at phi1. Let phi1 equal to 1 inside of T1 and equal to 0 on the boundary of T1 and 0 on the T2, whole T2. So phi1 only non-zero inside of T1 and 0 otherwise. Phi2 is equal to x inside of T1, 0 otherwise. So on for phi3. So 1 x, y, they form all the linear function non-zero on T1. Similarly, we have 5, 4, 6, which is associated V0 on T2, non-zero on T2, and 0 for the other points. Finally, we have phi7. Phi7 is equal to 1 on E and 0 otherwise. I like to point out all those basis functions they define on the whole unit square. For example, like U7. U7 define the whole unit square, but only non-zero on E and equal to 0 otherwise. Okay, next, let's see. Let's compute. So we find VH, we find our basis functions. Next, we are going to find weight gradient for those basis functions. Okay, first of all, weight gradient V belong to P0T square. And definition of weight gradient is on equation 12. And P0T square is like, it's a vector with 2 components. Each component is a constant. Obviously, dimensions 2 can be spanned as 2 basis functions. One is a 1, 0, another 0, 1. And weight gradient phi I belong to that space. So can be write a linear combination of those 2 basis functions. Example 1. Example 1. We're going to find the weight gradient for phi1. Phi1 have 2 parts, right? Which is weight function, right? Phi1 0, phi1b. Recall, phi1 equal to 0 inside of T1 and equal to 0 otherwise. Okay, what are we going to do next? In the equation 12, we're going to replace V by phi1. Then let Q equal to first basis function 1, 0. Then we got a first equation. Then let Q equal to 0, 1, second basis function. We got the second equation, which is a 14. Now let's see that. So on the left-hand side, you replace weight gradient V and weight gradient phi1 by this. Okay. Then testing Q 1, 0, 1, 0. Okay. So that gives us a left-hand side. Then let's look at the right-hand side. Right-hand side, V0 here is a phi1, 0. let V equal to phi1. Phi1 0 equal to 1. So we have 1 here. Then Q is 1, 0. You take a divergence, give you 0. Constant, you take a divergence, give you 0. Then plus phi1b. Remember, phi1 only non-zero inside of T1 equal to 0 on the boundary of T1. So phi1b is 0. So we got a 0 here. So 0 times anything 0. 0 times anything 0. So the right-hand side is 0. Now let's look at the left-hand side. Left-hand side, 0, 1, 1, 0. This gives you 0. Okay. Only this one, 1, 1. Okay. The function will 1, this inner product give you 1. Integrate on T1. So give you the area of T1. So left-hand side equals this. So equation 13 implies C1 equal to 0. Similarly, we can find C2 also equal to 0. C2, we got C2 just by testing Q by 1, 0, and 0, 1. So we find C2 is 0. Therefore, weight gradient phi1 equal to 0 on T1. And the weight gradient is local, totally local. It's computed on each element. So we have 2 elements here. So we need to find a weight gradient phi1 on T2. We can find a weight gradient also equal to 0 on T2 similarly. So you would, if we have 100 elements, that means you need to find a weight gradient of basis function on each element. However, fortunately, except 1 or 2 elements, the weight gradient for basis functions are not 0. Most of them, all of them are 0. For this one, it is 0 for all the elements. Similarly, you can see for I from 1 to 6, weight gradient of them, all zeros for this simple, for this special WG element. Okay, now let's look at example 2. This one where we want to find a weight gradient for phi7. Phi7 is different than phi1, phi2 to phi6 because phi7 is a basis function associated with VB. Recall phi7 equal to 1 on E on that diagonal and equal to 0 otherwise for all the other points on the unit square. So V7, gradient of phi7 can be write a linear combination of basis function for this one. And in the equation 15, which is the formula we use to compute weight gradient, let V equal to phi7, then let Q equal to 1, 0. We got a first equation here. Then let Q equal to 0, 1. We got a second equation. Again, the left-hand side is the same, the right-hand side. Now, phi7, 0. Phi7, 0 on T1, obviously is 0. Then phi7b, which is not 0, not always 0. Okay. Then when Q is 1, 0 dot n. 1, 0 dot n give you phi1, n1. Okay. N there is outward normal with the 2 components, n1, n2. And the phi7b, okay, phi7b on the T1, okay, this is a partial T1 with 3 edges. And the phi7b only non-zero on E and the 0 on this 2. Therefore, the partial T1 become to E and the N1. You integrate this to give you the edge of E times the N1. Then the left-hand side, this term is 0. This term again give you C1 times the area of T1. Therefore, our C1 equal to this. Similarly, we can find C2 equal to this. And therefore, you put C1, C2 back here. You're going to find weight gradient of phi7 equal to this sense. And the NE here is outward normal on E respect to T1. On T2, same thing, just replace area of T1 by area of T2, NE. This NE here and this NE here, that's the opposite direction. They're unit outward normal for respect to each element. Okay, so far we find the weight gradient for all the 7 basis functions. Therefore, we can find weight gradient phi I, weight gradient phi j. So we can form the first part. So we can see that's what we need to form. Okay, this is a matrix. So we're able to do the first part. So next, let's do how to compute the second part. Okay, second part, how do we find how to calculate stabilizers? Stabilizer for this case defined on the set 16. We do need the QB here because W0 or V0 is the first order polynomial, and the WB and the VB, they're 0 order polynomial. So we need to project first order polynomial to 0 order polynomial. For this case, V is a linear function. QB project to constant. That's simply equal to V evaluated middle point for V is a linear function. Okay, first of all, example 3, we want to find S phi1, S phi5. Recall phi1 equal to 1 inside of T1, 0 otherwise. Phi5 equal to X inside of T2, even 0 on the boundary of T2 and all other points. Okay, S phi1, phi5, by definition of 16, we just write them down. Okay. Now, as I said, phi1, phi5, they are associated, their basis function associated with V0, okay, equal to 0 on the boundary. So all the phi1b, phi5b, they're zeros. Same here. So this term is simplified like this. Now let's look at this one. 1, 0, phi1, 0 on T1. Phi1, 0 on T1 equal to 1. Phi5, 0. Phi5, 0 equal to X on T2 equal to 0 on T1. So we have 1, 0. And this one, phi1, 0 on T2 is 0. And the phi5, 0 on T2 is X. Then QBX. I mean, 0 times that give you 0 anyway. So S phi1, phi5 equal to 0. Example 4, let's compute what is the S phi1, phi2. Remember, phi2 is equal to 0 inside of T1, equal to 0 on T1, on the boundary of T1 and the other points. Okay, so let's find S phi1, phi2. Okay, what the first line, just use the definition 15, and we have 2 elements, so we have to do partial T1 and partial T2. Again, phi1b and phi2b, they're zeros. That's by definition. So now let's look at it here. Phi1, 0 equal to 0 on T2. So phi1, 0 is 0, phi1b is 0. So this term total is 0. 0 times anything 0. So we only have 1 term here. So this is phi1b is 0, phi2b is 0. We have this. So phi1, 0 on T1 is 1. Phi2, 0 on T1 is X. So X times 1, basically, we need to integrate the X on the whole partial omega T1. Remember, T1 have 3 sides, right? This one, I mean, this one, this one, this one. Let's do counterclockwise. So we have 1, 0 on this vertical one, then 1, 0 on this horizontal one, then on E, like this. So let's integrate this on the vertical one, 1, 0. And the x on this vertical line, x equal to 0. Then 1, 0, that's the horizontal line. X QB project the x, which means the x take middle point, which is the 1/2. Then on the third line, integrate e. We integrate this, we got this. So that's tell you what is S1, SV1, and SV2. So far, we were able to compute. We're able to compute this one and this one. In other words, we know how to compute this one. So we can form a linear system here, then solve it. We're going to show that this linear system is a symmetric, positive, definite. You solve it, find CJ, then you find your WG finite element solution.